Welcome to Cambridge IGCSE Physics, Lesson 30.1, Dispersion by Prisms. Today we explore how white light separates into colours when passing through a triangular glass prism. This fundamental optical phenomenon demonstrates the wave nature of light and forms the basis for understanding spectroscopy and optical instruments. We'll examine the physics principles, observe spectrum formation, and understand why different colours bend by different amounts. This core content lesson builds essential knowledge for your Cambridge IGCSE physics examination. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, describe dispersion of light by glass prism. This means explaining how white light splits into component colours when passing through triangular glass. Second, understand white light separates into colours. You'll learn that white light is actually a mixture of all visible colours combined. Third, observe spectrum formation and colour order. You'll recognise the sequence red, orange, yellow, green, blue, indigo, violet. These objectives align with Cambridge IGCSE core requirements and focus on fundamental optical principles essential for your examination success. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, dispersion, which means the separation of white light into its component colours when passing through a transparent medium like glass. This occurs because different colours have different wavelengths and bend by different amounts. Second, prism, which means a triangular glass block that refracts light. The triangular shape causes light to bend twice, once entering and once leaving the glass. Third, spectrum, which means the range of colours produced by dispersion, typically showing red, orange, yellow, green, blue, indigo, and violet in that order. Understanding these terms precisely is crucial for examination success. Let's explore our first core concept. What is dispersion? The fundamental principle states that white light contains all visible colours mixed together. When we see white light from the sun or a lamp, it appears colourless, but actually contains red, orange, yellow, green, blue, indigo, and violet light combined. The definition is, dispersion is the separation of white light into component colours due to different refractive indices for each wavelength. This means each colour bends by a different amount when entering glass. Key facts to remember: each colour has a different wavelength, with red having the longest wavelength and violet the shortest. Different colours bend by different amounts because glass has slightly different refractive indices for each wavelength. Red bends least because it has the lowest refractive index in glass, while violet bends most because it has the highest refractive index. The diagram illustrates white light entering the prism and separating into the spectrum of colours. Now we examine the experimental method. This follows Cambridge IGCSE standards for observing dispersion. The apparatus needed includes a white light source such as a filament lamp or LED torch, a triangular glass prism with smooth surfaces, and a white screen or wall to display the spectrum. The method consists of these steps. First, place the light source so it shines a narrow beam toward the prism. Second, position the prism so light enters one face at an angle. Third, place the screen to catch the light emerging from the prism. Safety is paramount. The main hazard is bright light, which can damage eyes. Therefore, you must never look directly at the light source or reflected beams. The diagram shows the complete setup with light traveling from source through prism to screen, where the spectrum becomes visible. Let's work through our first example. The problem asks us to explain why red light bends less than violet light in a glass prism. We are given the wavelengths. Red light has wavelength 700 nanometers, violet light has wavelength 400 nanometers. We need to explain the different bending amounts. Step 1. Identify the principle. The refractive index of glass varies with the wavelength of light, a phenomenon called dispersion. Step 2. State the relationship. Shorter wavelength light has a higher refractive index in glass. Step 3. Apply to colours. Violet light with 400 nanometer wavelength has a higher refractive index than red light with 700 nanometer wavelength. Step 4. Conclude. Higher refractive index causes more bending according to Snell's law, so violet light bends more than red light when passing through the prism. Example 2 examines spectrum formation and colour order. The problem asks us to describe the spectrum order from prism dispersion. The setup uses white light passing through a triangular glass prism. Now we analyze step by step. First, white light enters the prism as a single beam containing all colors mixed together. Second, different colors bend by different amounts due to their different refractive indices in glass. Third, the spectrum forms on the screen as colors separate spatially. Fourth, the order from least bent to most bent is red, orange, yellow, green, blue, indigo, violet. The memory aid, Roy G. Biv helps remember this sequence. The diagram shows the spectrum as it appears on the screen, with red at the top bending least, and violet at the bottom bending most. This consistent order occurs because wavelength determines refractive index. Mathematical skills are crucial for understanding dispersion quantitatively. Let's examine 3 key skills. First, refractive index relationship. Snell's law states that refractive index equals sine of incident angle divided by sine of refracted angle. When refractive index is higher, the refracted angle is smaller, meaning more bending toward the normal for the same incident angle. Second, wavelength and color relationships. Red light has wavelength 700 nanometers, orange 620, yellow 580, green 550, blue 480, indigo 450, and violet 400 nanometers. These values help predict behavior. Third, dispersion analysis. We can compare refractive indices. Violet has higher refractive index than red in glass. This allows us to predict bending. Colors with higher refractive index bend more towards the normal. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks you to list the colors of the spectrum in order starting from red. This tests your memory of the sequence we've learned. Question 2 is intermediate level. It asks you to explain why white light separates into colors in a prism. This requires you to apply the dispersion concept, mentioning wavelength, refractive index, and bending. Question 3 is advanced level. It asks you to compare the bending of red and blue light, giving scientific reasons. This tests your analytical understanding of the relationship between wavelength, refractive index, and refraction angle. For all questions, remember to show your reasoning clearly, use proper scientific terminology, and explain the underlying physical causes rather than just describing observations. Physics principles power our modern world. Let's see how dispersion applies in practice. In technology, spectroscopy uses dispersion to identify chemical elements in distant stars. Astronomers analyze starlight spectra to determine stellar composition, temperature, and motion. Each element produces characteristic spectral lines when dispersed. In scientific research, optical instruments like spectrometers separate light for detailed analysis. This enables identification of materials, measurement of concentrations, and study of atomic structure. In engineering, fiber optic communications must control dispersion to prevent signal distortion over long distances. Engineers design fibers to minimize unwanted dispersion while maintaining signal quality. Career opportunities include optics, engineering, designing laser systems, astronomy studying celestial objects, telecommunications developing communication networks, and medical imaging creating diagnostic equipment. Natural examples include rainbows formed by water droplets dispersing sunlight, diamond sparkle from internal light dispersion, and colorful patterns in oil films on water. Let's review the solutions to build your confidence. For question 1, the spectrum order is red, orange, yellow, green, blue, indigo, violet. The memory aid Roy G. Biv helps remember this sequence which never changes. For question 2, white light contains all colors mixed together. Each color has a different wavelength, which causes a different refractive index in glass. This different refractive index causes different amounts of bending, which separates the colors spatially to form the spectrum. For question 3, blue light bends more than red light. Blue has shorter wavelength at 480 nanometers compared to red at 700 nanometers. Shorter wavelength gives higher refractive index in glass, which causes a greater refraction angle according to Snell's law. Now for exam success tips. When asked to describe, state observable features clearly without explanation. When asked to explain, give scientific reasons using key terms like wavelength, refractive index, and refraction. Always use the correct spectrum sequence from red to violet. Link concepts by connecting wavelength to refractive index to bending amount. Let's summarize today's lesson on dispersion by prisms. The key points to remember are, first, dispersion means white light separates into a spectrum of colors when passing through a glass prism. This happens because white light is actually a mixture of all visible colors combined. Second, the cause is that different wavelengths have different refractive indices in glass. Shorter wavelengths like violet have higher refractive indices, while longer wavelengths like red have lower refractive indices. Third, the order is always the same. Red bends least and appears at one end, violet bends most and appears at the other end, with orange, yellow, green, blue, and indigo in between. For further study, review the spectrum color sequence until you can recite it perfectly. Practice explaining the dispersion mechanism using proper scientific terms. The next lesson covers total internal reflection, which builds on refraction principles by examining what happens when light cannot pass from one medium to another. Ensure you understand today's wavelength and refractive index concepts before moving forward.